All right, in this video, we'll take a look at momentum. Momentum is the product of an object's mass and velocity. What it measures is the strength of an object's motion. Objects with large momentums have strong motion, so in other words, it's difficult to change that motion. It's difficult to cause acceleration. If an object has a large amount of momentum, it's difficult to speed it up, slow it down, or turn it. Momentum does sound a lot like inertia, a concept that we covered back with Newton's first law. But there's one really big difference. Inertia is an inherent property of matter. All matter has inertia. Mass was the one thing that affected inertia, and mass is a vital part of the definition of matter. Matter is anything that has mass and volume. So if an object is matter, it automatically has mass, it automatically has inertia. All matter has inertia because it has mass. Not all objects have momentum. An object must be in motion in order for that object to have momentum. The amount of momentum that an object has is based on the mass and the velocity of the object. Mass and momentum are directly proportional. That means they change in the same way. An increase in mass causes an identical increase in momentum. So if I doubled the mass, that would double the momentum. If I tripled the mass, that would triple the momentum. If I had 1/4 the mass, I would have 1/4 the momentum. A decrease in mass causes an identical decrease in momentum as well. If the mass of an object in motion is doubled, again, the momentum would be doubled. Directly proportional means they will change in the same way. If the mass of an object is halved, the momentum is also halved. So again, identical increases, identical decreases. Mass and momentum are directly proportional. Velocity and momentum are also directly proportional. If the velocity of a moving object is tripled, the momentum would be tripled. Again, that same idea, that identical change. In equation, directly proportional relationships will be represented with having variables in the numerator of the equations. The equation for momentum is m times v. Both m and v are in the numerator of this equation because we can envision this as m times v over 1. Both mass and velocity are in the numerator of this equation, making them both directly proportional to momentum, which is abbreviated with p. Again, if I kept volume constant, if that was a 1 and it stayed 1, let's say I started off with a mass of 2, that would give me a momentum of 2. If I doubled that momentum to 4, or mass to 4, that would increase my momentum to 4 as well. Doubling the mass would double the momentum. Just a reminder, going back to the velocity equation as an example, and it did come up prior to this in one of our other equations. We're dealing with Newton's second law of the force equation. But again, it's a really important point to understand. If variables are inversely proportional, they end up in the denominator of equations. They'll end up on the bottom. So we go back to the velocity equation, and we want to understand how velocity is affected by displacement and time. Because displacement is in the numerator, I know displacement and velocity are directly proportional. If time stays constant and I double the displacement, that would double the velocity. Again, directly proportional relationships, the variables are in the numerator. And that relationship does go across the equal sign. It's telling you how these two things are related to velocity. So displacement and velocity are directly proportional. Time, on the other hand, is inversely proportional because it's in the denominator. If I were to double the time, make this number on the bottom twice as big, that would affect my velocity in the opposite way. It would be half the velocity. So again, just thinking numbers, if I have a displacement of 1 and a time of 1, my velocity is 1. But if I leave that displacement the same and I double that time, I will cut the velocity in half. It'll be 0.5. So any variable that's in the numerator is a directly proportional relationship with whatever's on the other side of the equal sign. Anything that's in the denominator has an inversely proportional relationship with whatever is on the other side of the equal sign. The standard unit for mass is kilograms. The standard unit for velocity is meters per second. So when you do the equation for momentum, masses should be in kilograms and velocity should be in meters per second. If they're not, you may want to consider changing those. When they combine together, we get a combined unit for momentum. Now, unlike with the force equation in newtons, this combined unit is not summarized as some nice little neat thing like newtons were. Remember, a newton was 1 kilogram meter per second squared. They took that kilogram meters per second squared and combined it together into a nice neat unit called a newton. The unit for momentum is not combined into something simpler. It just stays kilograms times meters over seconds. Kilograms meters per second is how you would read it. So let's do a little bit of math with this as we can understand some of these relationships a little better and how the equation works. The child on a bike has a mass of 35 kilograms. How much momentum does the child have when traveling 10 meters per second? The 35 kilometers, that's a mass, or kilograms, that's a mass. Kilograms measure mass, and it does say mass. 10 meters per second, that would be a velocity. Meters per second is a velocity unit. And we want to know what the momentum is. Momentum is p. Don't ask me why it's p. That's just what they decided. We only have one equation that has these three variables in it at this point. That is the momentum equation, p equals m times v. Substitute. The mass is 35 kilograms. The velocity is 10 meters per second. Multiply those together, you get 350. And then it's just kilograms times meters per second, just like the equation shows you for that. 350 kilograms meters per second is the answer. Pretty simple, pretty straightforward calculation. Let's compare the child's momentum to the momentum of the bike they're riding. The bike a child rides has a mass of 10 kilograms. How much momentum does the bike have when traveling 10 meters per second? Now already we know that this is a lower mass than what the child had. The child had a mass of 35 kilograms. The bike has a mass of 10. So knowing the relationship between mass and momentum and knowing that they are directly proportional, this decrease in mass should cause a decrease in momentum. So we should see a smaller number. Let's see what that actual number is. 10 kilograms would be the mass. Tells us that in the question, and it does have kilograms on it. 10 meters per second would be the velocity of the bike. And again, we're looking for momentum p. Only one equation right now that has all three of those variables in it. Substitute. Mass is 10 kilograms, velocity is 10 meters per second. Multiply those two together, you get 100 kilograms meters per second. So we went from 350 kilograms meters per second to 100 meters per second, kilogram meters per second. And you'll note the amount of increase or decrease in the mass, we went from 35 to 10, is proportional to the decrease that we saw in momentum. It went from 350 to 100. And it's a directly proportional relationship. Both variables change in the exact same way. Again, that is just a demonstration of the effect of mass on momentum, using the math to understand that. And like I've said before, if you're taking a test and you can't remember what the relationship is between two variables, you are given the equations. So you can look at the equation, throw some numbers into that equation, and calculate. Throw in a number for the mass and the velocity, and then change that mass and see what happens. And you'll be able to figure out the type of relationship that you have. That whole math problem can be applied to the real world. This unfortunate individual is flipping over the handlebars of a bicycle. And it's probably because of, at least partly due to what we just did mathematically. This is not a child, this is a person. The average adult human weighs 60 kilograms. So much, much heavier than what a bicycle is, a lot more mass than what a bicycle has. So if you were to jam on the front brakes of the bicycle and stop that front wheel, well, that front wheel and that bicycle will stop pretty quickly because they have a relatively low momentum. the force that's generated by that braking system is more than enough to stop the bike. But because the rider of the bike has 2, 3, maybe 4 times as much mass, they have 2, 3, maybe 4 times as much momentum. And they are not as likely to stop, and they continue moving on because of their stronger momentum. A good real world example of how this works. And the numbers from the math that we calculated there would pretty much support that. It's also easier why when you're shopping for groceries, it's much easier to turn the shopping cart at the end of the aisle when you first start shopping than it is when you're done. When you first start shopping, the shopping cart is empty. And if the shopping cart is empty, it has low mass. Low mass means low momentum. Low momentum means it's easy to turn. But once you've loaded it up with all these groceries, you've increased the mass of the shopping cart tremendously. And because you increase the mass tremendously, you increase its momentum tremendously, making it much harder to turn at the end of the aisle when it's full. So again, good examples to help you remember that relationship. Let's look at velocity now. A 1,500 kilogram car travels 4.5 meters per second. That's about 10 miles per hour. Not mpg, mph. How much momentum does the car have? Very similar problem. Doesn't say mass of this time, but again, kilograms measure mass. Meters per second measure velocity. We want to know how much momentum it has. Only one equation fits that at this point. P equals m times v. Substitute in 1,500 kilograms is the mass, 4.5 meters per second is the velocity. 1,500 times 4.5 is 6,750. And again, the units just get combined together into one big mess, kilograms meters per second. Much, much larger momentum than either the rider or the bicycle had, even though they're moving at a much smaller velocity here because of that much, much larger mass. That much bigger mass gives the car much greater momentum. Let's see what happens when we speed the car up. Same 1,500 kilogram car moving 13.4 meters per second this time. That is about 30 miles per hour. How much momentum does the car have? So again, kilograms measure mass. Meters per second measure velocity. We're looking for momentum. Only one equation that fits those so far. Substitute. It's going to be 1,500 times 13.4. 1,500 times 13.4 is 20,100 kilograms meters per second squared. We were moving 4.5 meters per second here and had a momentum of 6,750. Increased that velocity to 13.4 meters per second and had a similar increase in our momentum up to 20,100. And again, this has real world applications. This is why you have to slow down before you turn a car. As you approach a turn, you need to apply the brakes and reduce the velocity of the car in order to reduce the momentum. Going from 30 miles per hour to 10 miles per hour reduces the momentum by 13,350 kilograms meters per second. Because we have reduced that momentum tremendously, it makes the car much, much easier to turn. That's why if you take a turn too fast, a car is likely to go straight. It won't turn the way you want it to, and you'll end up off the road, or worse yet, hitting somebody head on. You have to slow the car down in order to reduce the momentum, in order to make the car easier to turn. And decreasing the velocity is the way you do that, unless you're looking to throw extra objects out of your car as you approach the intersection and start throwing seats and groceries and stuff out of the car to make the mass go down. The easiest way is just to slow the car down. Take a look at this. A 300-gram toy car is traveling 2.3 meters per second. How much momentum does it have? Doesn't sound much different than the last one. Grams measure mass. Meters per second measure velocity. We still want to know what kind of momentum it's got, P. But there is a twist in this, and hopefully you've seen it already. Right there. This mass is in grams. And to do momentum problems, we most likely are going to want our standard units of kilograms meters per second. This would give us grams meters per second, which is not very commonly used. So we want to convert the grams into kilograms. We can do that metrically, again, because that's what the metric system was meant for. It was meant for simple conversions. Grams are a base unit. So right here, we need to take it up to kilograms, which would be right here. That is 1, 2, 3 places to the left. Don't ever count where you start. Always count where you finish. So it's 1, 2, 3 places over to the left. Move the decimal point 3 places to the left. Put it right there. And you get 0.300 kilograms. Always watch for the units and unit cancellations, particularly if you're in an upper level physics class. That's the way the questions are made harder, making you look for those things and recognize those things. If we put 300 times 2.3 in here, we're going to get a much bigger answer. In fact, it's 1,000 times bigger. But it wouldn't be correct if we want to use 0.3 times 2.3, which is 0.7. And again, kilograms meters per second. Always watch for those unit conversions. Whenever I'm running multiple choice tests and I'm putting incorrect answers in there to throw students off, I'll put an answer there where I didn't do the conversion. So just because what your calculator said matches an answer doesn't mean it's the answer. Make sure you've checked everything out before you decide. Algebra is always a part of it. How fast would a 250 kilogram go-kart need to be moving to have a momentum of 1,625 kilograms meters per second? Kilograms measure mass, and that big mess, kilograms meters per second, measures momentum. This time I want to know what the velocity is, how fast it's moving. Same equation, because that's the only equation we have for momentum right now. Substitute. 1,625 kilograms meters per second equals 250 kilograms times v. To isolate my variable, I'm going to divide both sides by 250. When I do that, 1,625 divided by 250 is 6.5. I flip that variable over here to the left because that's where math teachers like it. So v, velocity, equals 6.5 meters per second. When I divide this side by the 250 kilograms, the kilograms will cancel out. And all you'll be left with is the meters per second as your unit. So again, a lot of students don't want to write their units down when they do math, but units are so helpful. They let you know if you set your equation up right. They let you know if you've done your math correctly. If your units don't cancel out the way they're supposed to cancel out, you know you haven't done your math properly. But if everything cancels out the way it's supposed to, then there's a good chance that you've done it all right. Let's take a look at this one. A 53 Newton bowling ball is rolled with a velocity of 13 meters per second. How much momentum does the bowling ball have? Sounds a lot like the bicycle, the child, the car examples that we did, but with one big twist. Newtons are not mass. Told you before, when it says newtons right before the name of an object, 53 Newton bowling ball, that's a weight. The 13 meters per second, that would be a velocity. We're looking for momentum. The equation for momentum is P equals m times v. And I don't have a mass. I have a weight. So I have to figure out how to turn that weight into a mass. The way I do that is with the weight equation from Newton's second law. Again, one of the ways we make physics problems more challenging is by making them multi-step problems. By making you have to go back to previous equations, previous knowledge in order to find a missing piece of information to do your calculation. And that's what we have to do here. Acceleration due to gravity is 9.81 meters per second squared on Earth, technically negative. But if we're going to make this negative, we would have also had to make the weight negative because mass is always a positive number. So if we do negative 9.81 meters per second squared here, we would have to make that weight a negative number, indicating its downward direction as well, so that we had a negative number divided by a negative number to give us a positive mass. We are going to divide both sides by 9.81. 53 divided by 9.81 is 5.4. The newtons and the meters per second squared cancel in a way that gives us kilograms. If you want to see how that works, or you don't remember how that works, go back and watch the video on Newton's second law. Now that I have a mass, I can put that number into the momentum equation along with this 13 meters per second to solve for that momentum. So 5.4 kilograms times 13 meters per second. 5.4 times 13 is 70.2. And again, the kilograms and the meters per second combined together. So watch out for the unit conversions. Watch out for those ones where you have to do multiple steps and use old equations to solve the problem. In higher level physics classes, those are pretty much the